Hi there and welcome to my lesson on electricity, Ohm's Law. Now, Ohm's Law is going to describe the relationship between the variables that we've looked at so far, but let's quickly look at each one of them again and define them so that Ohm's Law actually makes sense. Okay, one of the ones we looked at was called current. And current we saw is coulombs per second, okay? And a coulomb, let's define coulomb. Coulomb was 6.241 times 10 to the power of 18 charges, or because an electron is a negative charge, you can say so many electrons. So currents per second meant that a certain number of, and this now represents a group of electrons, okay, a very big group of electrons. It's a collective noun. A coulomb is a collective noun for a group of electrons, and current is measuring how many of these groups will pass a certain point every second, okay? And our unit for current is ampere, and A for ampere, but the symbol that we're going to use is I. I is going to represent current. Okay, then we looked at potential difference. Okay, potential difference. Okay, now potential difference measured the amount of energy that 1 coulomb will have. In other words, it was joule per coulomb. Okay, so how much energy does one of these coulombs have? And then the unit is voltage, and so, or volts, and so the potential difference is also sometimes called voltage. Often it's called voltage. Okay, and the symbol that we're going to use is a V. So that one is slightly more simple. Okay, and then we have resistance, and I don't look much at resistance. Resistance is, okay, so I've got a flow of electrons, and these electrons have certain amount of energy per electron, or more specifically per coulomb. Okay, now what resistance does is it converts the energy into a useful form, and resistance is joules seconds. The symbol for resistance is simply an R, and its unit is an ohm. So sorry, I didn't do this for volt. Volt, our the symbol that we'll use, or the unit is the V. For ohm, it is the omega sign. Omega is the unit that we use at the end of resistance. Now, what what ohm means is, if I had 1 ohm, I am saying something like 1 joule energy converted for 1 second. Okay, so that doesn't really help me much, but let's look at something like 2 ohm. 2 ohm can either mean I had 2 joule energy converted for 1 second, or it can mean I had 1 joule of energy converted for 2 seconds. Okay, so the larger the ohm value is, okay, the more joules are converted every second, or the in order to convert more joules, I will need more seconds. Okay, so increase in resistance is got to do with a higher energy output, or a higher energy conversion, let's rather say that. Okay, so what is the relationship between these in a electric circuit? So here once again we have a simple diagram representing an electric circuit where we have our source of electron flow called a cell, or in this case it would be a cell because it's only one. If there's more than one, it's called a battery. And I don't think I've shown in a video just exactly what this symbol means, but the shorter side represents the electron supply, in other words, the excess of electrons with a negative charge, and the longer side, the deficiency of electrons, so it has the positive charge. So we know electrons are being donated from this direction, so this is the electron flow, and current is in the opposite direction, so current is in that direction. And let me not write it here, but anyway, so we're going to look at current most of the time. So current is going to go in this direction. Okay, now if that is the direction of current, we would measure our EMF. In other words, what is the amount of joules per coulomb of electrons. We'll measure them over here. Okay, so the potential difference over the battery, that would be the voltage. Okay, so voltage is measured over the battery, and that would literally tell me each of the coulombs of electrons that come here, how much is the total energy that they will have once they leave the battery. Now, of course, as they come here, they have to spend their energy on the resistors, so that by the time he gets here, he's got nothing again. That's the idea. Okay, now since there's only one resistor, if I were to measure the amount of energy spent per coulomb at this resistor, these two will have the same answer. And it's fairly simple. Why? Because there's only one resistor to spend its energy at. Okay, and so in this system, we'll now be able to determine at what rate will electrons be flowing into this resistor. In other words, we'll be measuring how many coulombs pass at any point. Okay, because this is series, there's no break in the current, so this is a series circuit, and so we can measure the amount of coulombs passing any point. Okay, and how would we do that? Well, this is Ohm's law. The current is directly proportionate to the potential difference and indirectly proportionate to the resistance. Okay, so in other words, if I want to know what the current at this point is, I will literally go and look at the current I is directly proportionate to the voltage and indirectly proportionate to the resistance. Now at this point there is not any resistance, but since the current at this point and the current at that point, or even in the resistor, okay, the current must be exactly the same, which means I can measure the current at this point. Okay, if I measure the current at this point, I will have the current in this whole system, since there are no resistors in parallel. Now, using this relationship, we can go and calculate the resistance or the current in various branches when we have parallel. There's a lot of ways, and I'll look at some examples a little bit later, but let's just quickly see why is the current directly proportionate to voltage and indirectly proportionate to resistance? Well, remember, current is the amount of coulombs that pass per second, and we can think of it more or less as a type of a stream, just like we looked at a water stream. Now, does it not make sense that the more energy you have, the greater you can have the velocity? Okay. So if each coulomb has more energy, they can flow at a higher velocity. But since there's resistance in the stream, the higher the resistance, okay, the lower the current will be. So for example, if I look at my water example, flowing through a pipe, okay, the higher the water tank is, my water tank, okay, the higher this water tank is, the greater will be the potential difference. Okay, so an increase in potential difference, and that will cause the velocity that it will have here at the end, okay, the final velocity, to be greater, and eventually the final and initial velocity will be equal when there's a constant stream going, so that the velocity in the middle here will also be the same as those two. And so the higher this tank is, the greater the potential difference would be, which would increase the velocity that the water is coming down on. You can think, for example, of water pressure at home. You'll see in cities you've got often got high water pressure because the towers are very high, but sometimes in smaller towns where there's not a very high tower, the water tower, the water pressure isn't that high. Okay, but now if something were to obstruct the flow, if there's things in this pipe that cause resistance, the more resistance there is in, or the bigger these objects are, the bigger the resistance is that they cause. Okay, or maybe the thinner the pipe is, the more the sides of the pipe cause resistance to the flow compared to the amount of water passing through. So these type of things will reduce the velocity. So an increase in resistance will reduce the velocity of the water. And now don't get confused, the V's are standing for velocity, not voltage. Voltage is not influenced necessarily with an increase in resistance. Okay, but other than that, that is how it at least makes sense to me, why your current is directly proportionate to your voltage and indirectly proportionate to your resistance. In the coming videos, I'll now have a look at the effect on resistance in or current in parallel circuits, and then I'll also go and look at some examples. Thank you for watching. We'll see you in the next video.